So in the last few weeks, we've covered lots of concepts. So let's figure out how we can organize those. So we'll start with when we're looking at just one thing. So we'll look at the behavior of one object, or perhaps system, for combining things together and considering them just one thing under the Newtonian model. So the things that are really central here are the acceleration of the object. That's really what we mean by motion. We symbolize that, of course, with an A. It gets a vector arrow on top of it because it's a vector. And the accelerations, they arise because of net forces on the object. And we get from the net force on an object to the acceleration by Newton's second law. So the acceleration is equal to the net force on the object divided by the object's mass, and that will take us either way between these two concepts. And for the net force, well, that of course is the vector sum of all the individual forces that happen to be acting on this object. So if we look at those, we will add those up as a vector sum of all of the forces that happen to be acting on this particular object to get us the net force. And different individual forces we can have are gravity, which is generally synonymous with the weight. So the force of gravity is equal to the mass times 9.8 meters per second squared. So that's one type of force. Other forces we could have, I guess, are the spring force. And that is given by negative k, the spring constant, times however far we've displaced the spring from its equilibrium position. It's another force. We have the tension. If there's rope or string around, that could be a force on the object. We could have all the surface forces if the object is touching the surface of another object. And those forces are the normal force, which we generally denote as F sub n. That is the perpendicular surface force, and the parallel surface force is friction. And two different kinds of friction. We can have static, that has a max value equal to the coefficient of static friction times the magnitude of the normal force, or we could have kinetic if the two forces are moving relative to each other. And then the friction force is equal to the coefficient of kinetic friction times the magnitude of the normal force. And these two, of course, oppose motion. That's how we get the direction. What are the forces? Well, we just learned about a couple of other forces. These are forces which oppose motion through fluids. And we kind of learned that there's really only one force here, but just for ease of modeling it, we break it in to the drag force, which we model as 1/2 times the drag coefficient gamma times the density of whatever fluid it's going through times the cross-sectional area of the object that's moving times the square of the velocity, or rather the speed of the object. That's the drag force. You might also have Stokes force if it's going a little bit slower or it's a little bit smaller. That force is against the velocity, and it's just something, we call it B, times the speed itself. And if you happen to know that your object that's moving is a sphere, then you can be a little more detailed. You can write Stokes' law. You can get the magnitude as -6 times pi times the radius of the object times the viscosity of the material it's going through. So all of those guys are B times the speed. So just 6 pi r nabla, that's the B, if you happen to have a sphere. So here are all of our different forces, and we haven't actually talked about this, but it turns out that all of these guys here that I am enclosing in this red dotted circle are really actually just manifestations of a single force, the electromagnetic force. You don't really have to know that. It doesn't help us as we're modeling right here, but these guys are actually all the same forces that we just model in different ways for different situations. Gravity is different. It's actually an entirely different sort of force. But those are the forces that we have met so far. We can look at all the forces on an object, get all the individual forces, add them up as a vector sum, get the net force on that object, and then we can use that to find the acceleration. And if we've got the acceleration, well, we can get to an object's velocity. To do that, to go from acceleration to velocity, we take the integral of the acceleration. If we happen to have the velocity and want to go back to the acceleration, then we take the derivative of the velocity, will get us the acceleration. And if we've got velocity, we can go to position, which we symbolize as a vector in 3 dimensions as r. To go from position to velocity, we take the derivative of the position. To go from velocity to position, to go to position from velocity, then we take the integral of the velocity. So, figure out what we need to know about net force, add all those guys up, get the net force, use Newton's second law to get the acceleration, and bing, 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 we can get all the way down to position. There are, of course, some special cases here. So it's not always true, but if it happens to be true that we have constant velocity, so if constant velocity, that is neither the direction nor the magnitude, the speed is changing, then we can use the constant velocity equation. And that is the change in position over the change in time is equal to the velocity, if the velocity happens to be constant. What else can we do? Well, I guess we've also talked about speed. That's the magnitude of the velocity. So those guys are connected, and we have another special case. If the acceleration is constant, well, then we can go ahead and use the constant acceleration equations. And those are, the final velocity equals the initial velocity plus the acceleration times time. Final position is initial position plus the initial velocity times time plus 1/2 the acceleration times time squared. You can also get the final velocity is the square of the final velocity is the square of the initial velocity plus 2 times the acceleration times the change in position. Or you could also do the final position plus the initial position equals the initial position plus 1/2 the initial velocity plus the final velocity times time. So all of those are fine to use if we happen to have a situation where the acceleration is constant. We also have another one. If the acceleration is centripetal, that is pointing to the center of a circle, then we've got uniform circular motion, or something which, travels in a circle. And in that case, we have an equation for the magnitude of the acceleration. It is the square of the velocity over the radius, or we could do the angular velocity squared times the radius. So that is a special case when we happen to know the acceleration is centripetal. And if we've got that, well, then we know about the period. That is how long it takes it to go around that circle once. Then the period is equal to the circumference, 2 pi times the radius of the circle, over the speed. So here are the things that we've learned about a single object. You can start anywhere on this map and get to anywhere else on this map by just sort of following the little areas. So if you got velocity, you can take the derivative, get to acceleration. You can then figure out the net force. Or you can start over here with different individual forces, add up all the forces on an object in the vector sum, get the net force, get to acceleration, say, oh, I happen to have centripetal acceleration, so I'm in uniform circular motion. I can use these guys. Of course, there are some connections on here that we haven't laid out. These are sort of the ones, these connections will always work, but occasionally we'll have a case where we just do something so often that we can make sort of a shortcut. So for example, if our net force is creating a centripetal acceleration, well, we can just jump straight from net force by saying we have a centripetal force. And of course, it's only a centripetal force because we've already said, oh, it's a centripetal acceleration. It's causing a centripetal acceleration. Therefore, we can use all of our uniform circular motion equations. But if we do it enough, we say, I see the net force. I see it's pointed into the center. It's always perpendicular to velocity. I can just skip right here, not go through these. Similar thing happening with gravity and the constant acceleration equations. If gravity is the only force that we need to model, the only force acting on an object, therefore it's the net force. That is, if the acceleration is magnitude g, 9.8 meters per second squared, down, then we can just pop into the constant acceleration equations and just plug in g down for all of the accelerations in these equations. So that's the vast majority of the ideas that we looked at. Most of them, of course, are acting on just a single object at a time, so we look at things one at a time, but there are a few concepts that we haven't quite got onto this map yet. So we do have a bunch of math tools that don't really, go anywhere on this map, but we do use them. Let me put another piece of paper on here so I don't mark out my map. For the math tools, so these are things like doing integrals. That's where you take the integral of something, or derivatives. Taking the derivative of things, usually with respect to time. These are things like knowing whether something's a scalar, just a number, and how to treat that, or if it's a vector, where it has both a number and direction, maybe it has some components. If we've got the components, then we can use all of our right triangle math, use some trig, where we use sine of, say, that angle where you have the opposite and the hypotenuse, and the adjacent side, well, the sine of the angle is the opposite side over the hypotenuse. The cosine of that angle is the adjacent side over the hypotenuse. The tangent of that angle is equal to the opposite side over the adjacent side. We can use the Pythagorean theorem, which says that the hypotenuse, if we square that, it's equal to the square of the two different sides. All of those guys are useful math tools, which aren't really part of the Newtonian model, but we can, of course, use them in all these different places. When we're adding up the vector sums, well, then we have to look at how to split vectors up into their components, use these trig functions. If we're at acceleration and we don't happen to have constant acceleration or uniform circular motion, then we have to do these integrals and derivatives. So these are math tools that we can use to help us move in between bits of our map here. What else? Well, we also have, of course, sometimes we don't have just a single object that we're looking at, but we're looking at different objects. So if we want to move between objects, so we have one object and we're looking at the interaction between it and another object, or, of course, it could be a system. So a collection of objects that we're thinking of just one thing as, or, really that's what a reference system is. Or a reference frame, that's what we're looking from different points of view of different objects. Well, for those things you would use Newton's third law. So that's the action reaction pairs, or you could use relative motion to help you switch between reference frames. And that's where you say, okay, if I want to know what's A doing from C's point of view, then I can add up what's A doing from B's point of view and what is B doing from C's point of view. So that's how we move. Once we've used this map to figure out what's going on with this single object, that's how we get into an additional object, tell different things about what's happening with other objects as well. And then finally, well, here we have a model. What if we want to compare it to experimental data? So we're comparing our model here that we're using, the Newtonian model, and data. Well, that's where the uncertainty comes in. So you have uncertainty, you can have percent uncertainty. If you want to compare different types of uncertainty, and that is the uncertainty for a particular thing over its value that it's associated with times 100%. You know, you can also say if I get the value for something that I'm looking at by measuring it, then I get uncertainty by type B methods. If I'm averaging a bunch of data to get my value, then I use type A methods. If I'm calculating my value from different things, then I propagate my uncertainty. If I'm getting my values from a graph, so maybe the slope or the intercept on a graph fit, then I will use some kind of line fit statistics. So we in class have been using the line estimation function. So that's how we take what we learned from this model and compare it to data that we take in the lab. So here we've got pretty much everything that we have done so far this semester. We've got our math tools, we've got how to move in between different objects, we've got our model and how to get between forces and accelerations and positions and velocities, and then finally we've got how to compare what happens in the model with what's going on with our data. So that is how you can organize everything that we've done so far this semester.